Hi everybody. Welcome to Contemporary Software Development at Portland State University. Software is one of the most malleable materials that humans have to work with. Compared to physical media like metal, wood, or concrete, software is very easy to change. That malleability provides tremendous freedom and opportunity for the people who develop software. Software can develop over time to provide new and better solutions to the problems that matter to its users, especially when the users discover new problems that they look to software to solve. The act of refactoring improves the internal quality of code so that it is easier to understand, and therefore easier to modify with confidence. When paired with automated tests, code refactoring provides powerful tools for contemporary software development. In this slide deck, we'll get an introduction to code refactoring, discuss why it's important, and then go on a tour of various refactoring techniques and learn how they can remove smelly code from your program. There's a lot of territory to cover, and it might take a couple of screencasts to explore it all. So let's get started. All software aims to provide a solution to a problem that matters to somebody. And when that solution solves a problem well, people often want more from their software. And so software must evolve to meet the new needs of the people who use it. This often results in the code that implements the software growing in scope and complexity. Over time, more features are added as more people ask things of it. There are optimizations that are made to the code to improve performance and help it handle more usage. And also, more people contribute to the code. There are often more developers who each have their own view of the system and implement things in their own way. Now, there are some schools of thought that advocate for a large upfront design that aims to understand the entire system and solve all of the use cases all at once before you start writing any substantive code. However, these upfront decisions are made when we know the least about the system. We know the least about the problems that we're looking to solve. And in terms of the design and the quality of the design, it often seems that we're already done before we've written a single line of code, and that leaves no room for improvement or evolution. Agile software development advocates for designs and architecture that emerge over time. To achieve these emergent designs and architectures, developers iteratively improve the design to meet the needs of today and only focus on the most likely and immediate needs for the near future. What this does is it keeps your options open. Because the design and implementation are never really done, you can feel comfortable to change it at any time to meet the current needs. As you're thinking about design and architecture, keep in mind the YAGNI principle, which comes from extreme programming. YAGNI stands for you aren't going to need it. So in practice, this means that you shouldn't build things until you really need them. Try not to predict the future, but instead respond to the present. When you do take action, take it at the last responsible moment. Not too soon, and certainly not too late. Because remember, if you make an investment in something now, you are delaying building something else that might prove to be more valuable. Also, when weighing options about the future, it's healthy to ask yourself, well, will it really be more expensive to build it later than it will be to build it now? And if so, what makes it more expensive? Oftentimes you'll find that it's not expensive after all. It's just an interesting problem that you want to solve. So make a couple of notes and move on knowing that when it is time to implement that feature, you can go back and review what you already knew about it today. Now, to be clear, YAGNI doesn't mean that you should neglect the internal quality of your code. Code should be healthy. Code should be easy to understand. YAGNI is more about not implementing features or new functionality until they're truly needed. So, as software grew in scale, you had software that had more people contributing to it over a longer period of time. A practice called refactoring was codified. The essence of refactoring is making small changes with each new feature to improve a small piece of the design of the code. So these are really very small and often localized changes. Things like renaming a variable or a method to make its intent more clear, or replacing duplicate code with a single method. Taking a very long chunk of code and breaking up into smaller ones. Over time, these little improvements really can add up to a design which is cohesive and comprehensible by people who have been working on the code for a long time, plus people who are new to the code. We all acknowledge that refactoring is like any discipline in software development. It's not something that comes naturally at first to many people, probably everybody, and it's something that you need to practice and understand, and something that you'll get better at over time. Because let's be honest, when you write a piece of code, you're going to put your best work out there. People don't purposefully cut corners, and if they do, they don't feel good about it. So, acknowledge that refactoring is something that is responsive and that is something that all software developers can do and ought to do. But when you realize that you need to refactor, resist the urge to make large refactorings. Here again, working in small chunks helps you learn and get feedback along the way. And a great way to get feedback is via a robust suite of automated tests. As we've learned about in other parts of the course, automated tests are essential to gathering feedback to make sure that your code still behaves as you expect. And as you're making refactoring changes, automated tests will also tell you if you've inadvertently made a change that breaks something. So along with refactoring, Martin Fowler and Kent Beck also defined something called a code smell. And a code smell is a signal that you should have a conversation about refactoring. Code smells are defined as a surface indication that usually corresponds to a deeper problem in the system. The nice thing about code smells is that they're usually pretty easy to spot. Right, we've all done it. We've looked at a piece of code and we've said, this doesn't seem as good as it could be, or this is a little hard to understand. Even someone who maybe is still pretty new to coding can look at a piece of code and say, I don't get that. So what can we do to improve it? Now, to be clear, a code smell isn't always a problem. It's more like it's a hint that something might be wrong and something warrants further investigation. And to be clear, if there's a smell in your code, it doesn't mean that you're a bad coder or even the code is bad itself. Again, it's just a sign that it might be worth investigating a little bit further to figure out if there's a way to improve the code. So be pragmatic about code smells. I've encountered people that want to clean up every code smell or run some automated tool that generates a report and says, there are hundreds of smells in your code. Be pragmatic about it. Look for the places that are impactful and look to make small progress every day as opposed to stopping the presses and trying to write everything all at once. With code smells, they're meant to engender a conversation, thoughtful questions about what is this code really trying to do and how can it better express its intent so that a human can understand it. Clearly the machine can understand it already. Because ultimately, by identifying and appropriately remediating code smells, you'll refactor your code to have a code base that has not only internal quality but also internal cohesion so that it's readable and consumable by others. So what are some examples of these kinds of code smells? We'll see lots of them throughout these slides, but here are a couple of categories that are meant to represent code smells. So let's say you have some names, variable names, method names, class names that are confusing or unclear. When you see code that's duplicated in multiple places, or it's mostly duplicated, that's an opportunity to say, hey, can I clean that up and only have that logic defined in one place so that it's easier to understand? So that it's less likely to have one copy of the code have a defect that's not present in another. Another kind of code smell is program elements that are long, that have a lot of cognitive overhead to read and to understand. Because it's really difficult to get your bearings when you're looking at dozens of lines of code. Another example is methods that have a long list of parameters. Because when you're calling these methods, it's easy to get the order of parameters wrong or have to understand, what does parameter 6 mean exactly? It's just more difficult to deal with. Other examples of code smells are data that is stored in global variables. Is there a way to better encapsulate it or to keep that data closer to where it's used? Mutable data that can change, especially when it's accessed by multiple threads, is something that's code smell. We all know that leads to race conditions and other kinds of programming problems. Another code smell is an indication of tight coupling within the system, meaning that when you change one part of the code, you're also forced to change another part of the code. That seems unrelated. When you see specific types of data being stored in a more general data type, so representing a phone number as a string instead of a phone number class, might be an opportunity for refactoring to make the intent of your code more clear. When you have complex logic in an if or switch statement, or that you have code comments that are redundant with the names of the program element that it's commenting on. So those are code smells, but what is refactoring exactly? Well, Martin Fowler puts out two definitions of it. The first one is a noun. Refactoring as a noun is defined as a change made to the internal structure of software to make it easier to understand and cheaper to modify without changing its observable behavior. You can also define refactoring as a verb, meaning to structure software by applying a series of refactoring without changing its observable behavior. In this definition, Fowler explicitly calls out small steps that preserve behavior. Right? We're not changing the external behavior of the system. The user should see no difference. Instead, these are internal changes that should make the job of the coder easier. So these aren't big bang changes. It's not code restructuring, it's code refactoring. And another key aspect of refactoring is that the code, if it is broken, it doesn't stay broken for very long. So yeah, there might be a few moments where you have a compilation error or you have a failing test, but it's not something that stays broken for days at a time. As a result, you spend a lot less time debugging the changes that you make with refactoring, and more time taking smaller steps towards an improved codebase. Now, refactoring is most effective when it's considered its own coding activity. Remember when we learned about unit testing and test-driven development and we had the red-green refactor? That's very much on purpose. So refactoring really ought to be separate from adding new capabilities. So a good guideline is when you're writing code, get it working first and have a test that validates that it's working, and then deliberately invest time in cleaning up the code. As you're refactoring and looking at the code, avoid the immediate temptation to fix a bug or to modify behavior that you know isn't working. Instead, make a note of it and have that be the next unit test that you write. To keep refactoring compartmentalized and small batches, you want to focus just on making the code better from a human standpoint, not necessarily adding new capabilities or even fixing a bug. Unless the refactoring really requires it, the tests that work with your code shouldn't change what they validate. And if you can achieve this working in small batches, it means that you'll never go more than about 10 minutes without refactoring the code, or at least looking for an opportunity to refactor the code. And this is how you make a clean, healthy code base, is that you do a little bit each time you make a change to retain the overall health of your code. So what are some examples of refactorings? We'll go into a lot more detail later, but here's an overview. At the end of the day, most of these refactorings, really all they do is they move code around so that you have a clearer, more cohesive, more understandable code base. So things like extracting code into its own method and giving it a good name, or extracting a code within a method into a variable to help understand and express its intent. Another set of refactorings are kind of the inverse of that, which is inlining methods and inlining variables. Sometimes methods outlive their usefulness, or a design that had methods or variables of a given name, or just even had them at all, is no longer fit to purpose, and so it's perfectly fine to replace a method with just the code that it calls. Over time, method signatures, the name and the parameters, can grow to be unwieldy, or as more capabilities are added to a method, or as a method does more things, the name is no longer appropriate, and maybe the arguments get to be too long and too confusing. So modifying method declarations is another very common refactoring. And the way you do that is by changing the names of things and also maybe replacing a long list of method arguments with a single object called parameter object that contains all of that information. So we just talked about the fact that refactoring doesn't change the code. It doesn't offer new behavior to the user. It doesn't make things faster necessarily. So why do it? What are its benefits? Well, ultimately, the consumer of the refactoring is the developer, is the person who writes the code. And so then when code is better refactored, it expresses its intent more clearly, which then helps you understand the larger design. As a result, it's easier to modify the code in the future because you know how it's organized. You can more quickly identify what code ought to change when you want to add a new feature. Well-factored code expresses what the author wants out of the code, not just what the author told the code to do. And this is a really important distinction for someone who is a human and is reading the code. Refactoring also often reduces complexity. There's just a lower cognitive load to understanding well-factored code. And why? Well, because well-factored code clarifies its assumptions. And as a result, it's less likely that you as a coder are going to introduce a new bug because you understand how it works. Also, there's a lot less code archaeology. I think we've all experienced that, right? We see a code base for the first time, or maybe revisit a code base that we wrote a while ago, and we have to, what I call, page all of this stuff back in, right? We need to re-understand, relearn how the code is organized, what various methods do, how objects relate to one another. The better you refactor your code, the less cognitive load there is to understand it. And because well-factored code has high internal code quality, it leads to high external code quality because you can go fast in it. And the code has what Martin Fowler calls stamina. It allows it to run faster, to change more quickly, and over a longer period of time. Now, when are some times that you should consider refactoring your code? Well, it can happen at any time. But when you start a new feature, maybe you come in for the day and you're trying to figure out what you're going to do first. A good way to familiarize yourself with the code, or maybe refamiliarize yourself with the code, is to look for opportunities to refactor. Again, this is exploring the code base, helping you as a developer understand what it's all about. So for instance, look for code that can be moved into a shared superclass, or move a common code or reused code that can be put into a shared method. The analogy here is like checking the map before you go on a journey to understand, well, what's the fastest route to where I want to go? Another good time to refactor is when you realize there's something you don't understand, where you're looking at a piece of code and you admit to yourself, it's like, I don't understand this. What is all this stuff doing? And that's usually because of complexity within the code. I'm sure it made sense to the original developer at the time, who might have been you. But when you come back to the code, look for opportunities to extract a complex if condition into a method that has a clear name. Or to take a method that's grown pretty long and break it apart so that you can see the steps that it goes through. Because basically what you're doing is taking all that learning that's in your head and putting it into the code. You could just try to keep it in your head, which is really hard to do as you learn more and more things. You could write it down in a separate document, and sometimes that's fit to purpose. But refactoring advocates for making the code self-documenting, for lack of a better term, so that anybody who sees it can read it and understand. And finally, if you just have concluded that the code that you're looking at is convoluted, which happens, this is a good time to refactor. But I'd recommend that you start with the easy stuff. And that might be enough for now. Because big changes to code, rewrites and restructuring, that's expensive. Even when you do have good quality unit tests that provide coverage, it's still a big lift. And it's much easier to take a lot of small steps than try to make a giant leap. Now, like any optimization that you make to the code, if you refactor too early, before the code is stable, before it's been well tested, you might waste a lot of time. So there's a delicate balancing act for all of these things. And the reason that this is because when you haven't gotten the problem solved yet, when you don't have all the tests passing, you don't understand the whole picture. And you need to understand the scope of what you're currently working on before it makes sense to invest in moving the code around so that it can be more readable and accessible in the future. I always look to the mantra from extreme programming, which is do the simplest thing that could possibly work. You get it working, and then go back and improve the solution. And while refactoring does improve the readability of the code and makes it look nicer and everything like that, you should focus on solving the problem. That's ultimately what we're here to do. We're not here to write the perfect code, and certainly not out of beauty or pride. People use your software because it solves the problem for them, not because it is the best looking or best structured internally. Now, to be clear, refactoring isn't just for ugly code. Even code that is awesome, that solves its needs today, that is already well factored, will need refactoring over time because we learn more. And as we're implementing features, we all make decisions and trade-off. This is just how you get stuff done. You don't want to be stuck in analysis paralysis. Also, as part of coding, you make experiments. You make hypotheses. Like, if I design it this way, then it'll come out with an outcome that's positive. Sometimes those decisions don't pay off, and you have to acknowledge that and go back and fix things to make it better. And also, you have to realize that all code is created at a point in time, and something that made a lot of sense in the past might not be fit to purpose anymore. Sometimes this is using a framework that's gone out of vogue, or maybe has problems that have been identified with it. But it also happens on smaller things, the names of methods or the practices that you follow. This is okay. It's not that you got it wrong before. Ultimately, if software solves a problem for somebody, that's what right is. It's just that we've learned things in the meantime, and there might be better ways and more effective ways of expressing the code right now. So don't be too hard on the person that wrote the code, especially when that person is yourself. Acknowledge that you know more than you did in the past, and it's time to apply that knowledge. Because over time, if you keep a code base well factored, it becomes easier to work with, easier to change. Kent Beck had a pretty deep quote related to this. He said, "Make the change easy," which itself can be difficult, "and then make the easy change." And for me, I interpret this as saying, listen, along the way, you need to make a bunch of little decisions, which aren't always easy to make in the moment. But then once you do, subsequent changes become more easy. Now, you might think, oh, wait a second, I'm investing my time in what someone's paying me to do is to write code and solve a problem for someone. How do I justify writing anything but that code that solves the problem? Because won't this just slow down feature development? Actually, it's quite the opposite. The purpose of refactoring, again, isn't to make beautiful code or isn't meant to make the most perfect code. It's to help developers go faster, both in the present and in the future, and have them expend less effort because the code is easy to work with, because it's very well understood. However, we need to be pragmatic. So if you're about to implement a new feature, ask yourself, well, if I've got a refactoring in mind that I think will take me 3 hours to get working, if it's only going to take 1 hour to implement the feature otherwise, does it really make sense to invest in that refactoring right now? Sometimes the answer is yes. Sometimes it does make sense to invest in refactoring right now so you can go faster very soon. But sometimes it doesn't. This is one of those decisions that professional software developers have to make. And if you're advocating for refactoring with someone who controls your budget or with your customer, it's much more effective to make this economic argument than it is to extol the virtues of clean code or this is a best practice. Now remember that refactoring isn't supposed to change the external behavior of your software, but sometimes it does. Right? Usually this is, it doesn't compile anymore, or there's a piece of code that, you've inadvertently deleted. And this is why it's good to work in small batches, right? You make these small little changes, and then it's easier to identify what caused a breakage. And of course, identifying the breakage is made easy when you have a fast-running suite of comprehensive tests. It gives you that feedback, and then allows you to refactor with confidence. Similarly, there are lots of tools for refactoring. All modern IDEs have the ability to perform many of these refactorings, and depending on the language, you can do so really quite safely. But there are some refactorings that are too complex for a tool to identify and help you with, and that's okay. If you have a suite of fast-running tests, you'll get that feedback that you need right away, and you'll be able to make changes confidently. This is why refactoring is such a crucial element of test-driven development. Test-driven development could just be, writing a test that fails and then making it pass. But by adding that third phase in there, not only do you end up with code that works, you end up with code that works and then is extensible in the future. Tests can also be used to validate your understanding of the code before you refactor it. And this is actually really quite powerful. One of the things I often do is as I'm looking at a piece of code that I don't understand, I'll write a test to validate that understanding. Because I'm like, if I provide these inputs, does it get this output? Oh, it doesn't? Well, I guess that means I don't understand it. And by starting with passing tests with good code coverage, meaning that it exercises the complete logic of the code, it's much easier to move that logic around, to make changes to it, to simplify it without inadvertently changing its behavior. Okay, that's an introduction to refactoring. The remainder of these slides introduced refactorings in the context of code smells. So what we'll do is we'll first talk about a code smell, and then we'll talk about some refactorings that we can perform to alleviate or remediate that code smell. Now note that very often a particular refactoring can apply to multiple smells. And so you'll see that for a particular code smell, I'll list off some of the refactorings that can help with it, and you'll see that some refactorings are mentioned multiple times. We'll start off with a couple of code smells that are very general. These kind of code smells can appear in any programming language. So we'll talk about comments as a code smell, and then we'll talk about how to respond to a long method when you see it. Now, comments. We all use comments. We all learned about comments, and it's probably one of the first things that we saw in our initial computer science courses. However, as code bases grow big, and as software developers mature, we found that code comments are often, well, what Martin Fowler calls deodorant over the smelly code. Comments are only necessary when the intention of the code that they document isn't clear. And so this is the challenge that's faced by the software developer. Is there something that I can change in the code to make that intent more clear in just code, without having to write English to explain it? Now, to be clear, not every comment indicates that there's a smell in the program, right? There are certain kinds of comments, like Java.comments, that convey what an API does. That's really important to know because the person consuming the API doesn't necessarily have access to the code. And you certainly don't want to put the cognitive load on the consumer of your API to understand the implementation of your API when all they want to do is to understand how to interact with it. Comments are also appropriate when they reference some piece of documentation or the source of where someone learned about a particular algorithm. So not all comments are bad. However, if you see a comment that details how a piece of code works, that might be an indication that there's an investigation that's warranted, because that's kind of a smelly comment right there. So if you encounter a comment that seems smelly, consider using one of these refactorings. Something like extract method. This is where you would create a new method that has a meaningful name that can replace the comment. Or maybe changing something about the method declaration. Renaming the method or the names of the parameters to, again, make the intent more clear instead of adding a comment. Or introducing an assertion. So this will convey something that you know to be true or you believe to be true, some certainty that you have, conveying that in code instead of a comment. So now let's dive into what each of these refactorings means. So in the extract method refactoring, we take a chunk of code and move it to a new method and then call that new method instead of referencing the old code. This refactoring makes sense when you've got a large method or a large other piece of code that covers many, many lines. Also, if you've got a chunk of code that's duplicated in multiple places, makes sense to put those duplicates in one method and call that same method from both places. Also, when you've got a chunk of code where it's hard to understand what its intent is, why it is the developer who wrote it chose to do so. Extracting a method can really help clarify the intention, the what of the code, especially when the implementation or the how of the code is really complex. One side effect of extracting methods is that you end up with a lot of small methods. Anything that has more than a dozen lines all of a sudden feels a little smelly, feels a little bit awkward because you're doing a lot. And is there an opportunity to use better naming or better crafted method signatures to better express your intent? So again, when you feel the urge to write a comment that explains code, instead think about extracting that code to a method that has a more informative name and more informative parameter names. But if you find you can't come up with a good name, especially if you've tried a couple of things, that might be an indication that maybe the code isn't ready to be refactored. Because again, if it's hard to express the intent, maybe it just means the code needs a little bit more time to percolate, and then its intent will become clear. Or hey, if you've got a pretty good name in mind, if it's good enough, just go for it now. Don't spend too much time trying to make a decision. Do the best you can right now and go on to more important problems. You can always change it later. So how exactly do you extract a code fragment into a method? Well, you create a new method and give it the name that you believe clearly expresses its intent. Then you take the code that you want to extract, copy it into the new method. and replace that extracted code with a call to that new method. And of course, if there's data that it needs, you need to pass that in as parameters. So anything that's outside that block of code that was copied. And then, of course, that new method might return some data that the extracted code created. Then you compile the code and you run the unit tests. And also, it's a good time to look for other places where that same code might exist and replace it with that method call. So that was the extract method refactoring. Here's another refactoring that might come in helpful when you see a smelly code comment. And that's changing the method declaration. Now, method declarations are the API. It's the intersection point of our code. And if you think of the intersection point as a highway or as a road system, when you have an intersection that's difficult to navigate, you get congestion. And we've all done that. We've looked at code and we see a method call and we're like, what is that? What does that do? Luckily, if we control both sides of the method, the code that calls it and the code that implements it, it's pretty easy to modify the intersections to ease that congestion. And just to emphasize, we've been talking a lot about naming, but when you have a method that is well named, it lets the reader know what the method does, and lets them know that without them having to read and understand the code. Now note that as methods change to meet new needs to do more things, you have to change their names also. There's nothing wrong with that. And if you've got a good name for it, make the change, because making the name more intuitive now will reduce the cognitive load for the next person that uses that method. Beyond the name of the method, this refactoring also focuses on the parameters and how they can more effectively convey their meaning. For instance, sometimes it's more effective to use a more specific parameter type to make the intent of the method more clear. So consider a method called calculateAge. Is it better for it to take a person object, or is it better for it to be more general and take a date object? Without seeing the rest of the code, it's hard for me to know. You should do what's fit to purpose. But by using the appropriately broad parameter type, it can help keep your code decoupled, and you end up with functions that are more general and therefore more broadly applicable. But again, there aren't hard and fast rules for this. This is another one of the situations where today's choice might not necessarily be the right one in the future. And that's okay, because again, software is easy to change. Now, sometimes changing a method declaration is pretty straightforward, right? Yeah, rename a method, maybe a couple of its calls, or all of its calls, and this can be done pretty quickly. Again, working in these small steps, it can lead to fewer errors, but sometimes you have an intermediate step, which is kind of awkward because you're in the middle of refactoring. Changing parameters has a slightly larger impact to the call sites. Maybe you are adding a new parameter or changing the type of a parameter, and so you have to go back and make sure that each of the calls to that method have been updated to use those new parameters or new parameter types. So in this case, a good technique is to extract the code to a new method that is then called by the old method, and then visit the call sites of the old method one by one to update them to use the new method. Now, of course, if the method that you're refactoring is part of an API that's used by different code bases, you may need to mark the old method for deprecation for a period of time as a signal to the consumer that they shouldn't be relying on it anymore because it'll change in the future. Here's another refactoring that is relevant when you've got smelly comments. Now, as you're writing code, you make assumptions about what you believe to be true. And very often, these assumptions are implicit. They were things that were just in your head and you didn't even realize you were making them. Or maybe it's something that can be deduced by looking at the code, but they're not explicit. Making those assertions explicit, however, can really help the clarity and understandability of the code. We talked a little about assertions as part of the Java programming language very early on in the course. And so recall that when you have a failed assertion, it indicates a bug in the code, that the programmer made an assertion that turned out to be false in some scenarios. Because again, assertions are all about validating internal logic of the code, not external inputs that are provided by the users. So ideally, assertions should have no side effects on the program. The program would work exactly the same without it. And recall that the assert language feature in Java is a no-op at runtime unless you've explicitly enabled assertions in the JVM. And again, while assertions are valuable for error checking and debugging, the real value comes in the communication they provide to the reader of the code. But you should use them appropriately sparingly. Right? You don't need to have an assertion for every place that something needs to be true. Assertions are most effective when they convey something that needs to be true, ought to be true, or is assumed to be true. Also, the placement of the assertion matters. So for instance, let's say you have a value that has a setter method. Making the assertion in the setter method will tell you who set the surprising value in the code. This ultimately is much more valuable than asserting something about the code when the value is read, because you don't know how it got in there in the first place. And just to be clear though, while assertions do provide a runtime check on the correctness of the code, they are not a substitute for unit tests. Unit tests describe the scenarios in which the code should be used, and they benefit from assertions, but you really need both in your system to be confident that you have covered all of the relevant use cases. Let's take a look at another code smell, which can happen in any programming language. And those are long methods. Now, as we've probably all experienced, long methods are difficult to understand. You're looking at the code, and it's hard to keep all the details in your head. Long methods are also much more likely to contain duplication. Now, back a long time ago, there was a legitimate concern about short methods because there was a perception that in many instances was true that the runtime systems of the time, and the CPUs, the compilers, it was more expensive to call functions than it was to have one big line of code. However, that hasn't been true for many years. And so the argument that a longer method will perform more effectively at runtime just really doesn't hold water anymore. Also, with tools like IDEs, it's so much easier to navigate code than it used to be. And so you can go back and forth between various method calls very quickly. So really, shorter methods are the right thing to do now. Just like what we talked about in the extract method refactoring, when you've got a long method, you can extract methods from it, and if you name them after their intentions, all of a sudden the code becomes much more clear and easier to understand. So again, extract a block of code to a method with an effective name instead of writing a comment for it. Additionally, if you've got a piece of code that has really complex conditionals for its if statements or its loop terminators, that might be another signal that the code could be refactored. So here are some refactorings that are effective when you encounter a long method. The first one is extract method, which we've already talked about. This is where you take a big long method and turn it into many smaller methods and call those instead. And this is usually sufficient, right? This is a refactoring that I use all the time when I encounter a large method. Another effective refactoring for long methods is called replace temp with query. And basically what this does is it extracts a method to initialize a variable. The introduce parameter object refactoring will take all the inputs to a method, all the parameters to a method, and put those together in an object of its own. So the method only takes one object that contains all the data that it needs, instead of a series of multiple ones. Similarly, preserve whole object refactors code to send an entire object that has several values that the method being called needs, instead of sending in those values individually. And finally, the decompose conditional refactoring moves complex conditional logic into a method. So let's take a look at these refactorings. So replace temp with query. These terms temp and query really just mean temp as a variable and query as the code that initializes the variable. And so we have variables in our programs so that we can create a value once and then use it later, maybe multiple times. So these are a little different from, let's say, loop variables that are modified over time. Temp variables are initialized once and never really modified. When it takes a lot of heavy lifting to compute the value for one of these temp variables, it might make sense to take that logic and move it into a method of its own. This has the benefit of taking a long method and making it a little bit slimmer. It also creates a nice boundary between logic. There's the method that consumes the information, and then there's the method that produces the information. It also helps you understand the dependencies and the coupling among that particular piece of code. And if you have to have that same logic in another method, then you can reuse the extracted method in that other place. Now, sometimes in code, you've got data that always seems to travel together. So you've got several variables or several values or several objects that end up all getting passed the same methods all the time. So the introduce parameter object refactoring says, well, take all those individual pieces of data and just group them together into one object of their own. This has a great impact of reducing the length of parameter lists, and also make sure that you have consistent terminology across multiple method calls, because you're using the terminology from that parameter object instead of relying on different variable names that ultimately get passed into one method that has a lot of parameters. Because you're creating a new class, a new object, it allows the abstraction that is represented by that data to be represented more concretely. And over time, you might find that that representation, that abstraction, grows to sort of have a life of its own because that data is related. By grouping that data together, you can really simplify the problem domain and how you've represented it into the code, because all of the related information is right there. So how we perform this refactoring, it's pretty straightforward. What you do is you create a new class that holds the data. That class probably starts out pretty simply, right? It just takes a constructor that has that data and probably provides getters. Maybe you'll need setters for them, depending on how that code is used. This kind of very simple class creates instances that are called value objects. Again, very little behavior on it, you just get the data that it has. Once you've created a new class, then you use the other refactoring, change method declaration, to change the method from having multiple parameters to just having one. And again, depending on how many calls there are, maybe you just sort of do one thing at a time, right? So you add parameter for the value object, retain all the other ones, and then one by one move the subsequent parameters into the value object and replace the usage of those parameters with information from the value object. Now, the preserve whole object refactoring is for a specific scenario where you have a value object already that contains several pieces of information. And when you have a method call that maybe takes 3 parameters, and so you ask that value object for those 3 parameters and then you pass them in. Because there's already an object that has that data, it might make more sense just instead of passing those 3 pieces of data in, you pass the entire object in. As a result, once again, you've reduced the size of the parameter list. You might find that the callers of the method have some duplicate logic, getting those parameters from the object. Maybe they perform a little bit of operations on them to then massage them to send to the method. Well, maybe that's something that can be moved someplace else so that logic isn't duplicated. Another situation to look for, which is very likely smelly code, is when you have a piece of information that an object has and it ends up going back to itself. In that case, it doesn't make any sense to have that data leave the object only to come back. Instead, you should just use this variable to reference that data from itself. Now, there's a caveat to this refactoring, though, because you may, by passing the object in instead of the data the object refers to, you might create a dependency which might not make sense. Meaning that the method that you refactor to take that object now depends and knows about that very likely more specific type of object, which might make other aspects of your design more difficult to work with. So just take a moment to consider the impact of this refactoring and ask yourself if it will break encapsulation. And finally, there is the decomposed conditional refactoring. Now, when you've got conditional logic, it's often kind of complex. Think about an if statement. How many components, how many things are ANDed together, ORed together? How many methods do you have to call to determine whether or not you want the true branch of that if statement or the false branch of that if statement. And as the complexity grows, we often lose track of why it is that we need all of that conditional logic. So in this refactoring, what you do is you take that logic that is there in an if statement or a switch statement or a loop terminator, and you move it to a method, and you give it a name that describes the condition that you're looking to meet. When you do this, not only do you make the code smaller around the if statement, but it makes it much more easy to read, and it takes all that complexity and moves it off someplace else. Once you've refactored the contents of the if statement into a method, it often makes sense to look at the body of the true and false branches to see if that code can be refactored into a method, again with a really good name that explains what it does. And once you do that, all of a sudden, that ternary operator that we learned about, where you have an if statement, if then else statement in a single line, all of a sudden becomes more compelling. Because when you have broken things up into methods, your if statements read more like sentences as opposed to a choose your own adventure book. And I think this is a good place to stop for now. We've learned about the motivation for refactoring and the benefits it can bring to the code, the people who author the code, and the people who use the code. We walked through a couple of smells and saw some refactoring techniques that can help reduce or eliminate those smells. In the next screencast, we'll continue our exploration of smells and refactorings with a focus on object-oriented code and how refactoring can improve classes and objects to make them more effective. Thank you for joining me on this introduction to refactoring as part of contemporary software development here at Portland State University.